Okay, so we're going to go to Vensim. I have a slightly different version than do you. And so you'll see slight differences between, it's mostly differences in icons. So what I'm going to do is, just to speed things up because we have limited time right now, I'm going to actually ask you to download something from the Moodle site. If you go to moodle.cs.ucs.ca, I've actually put a model there up for us. We'll be building plenty of these models, so there's no worry. But we'll download this one just to kind of get us started because we don't have time to see both packages unless we look at a pre-existing model. Okay. I think we built this up in about 45 minutes in a previous class. This is actually from the class last year that we built up. 858. Oh, you don't see it? Oh, God. Did I put it in my... okay, maybe it's hidden. Give me a second. First Vensim model. It's so under example models. Yeah. Oh, okay. Yeah. So you can download it, and it should be a so-called MDL file. It's a Vensim model file, and you can go open it and go find it. That's a Vensim model. So ladies and gentlemen, this is a simulation. It's called a system dynamics model. System dynamics is a modeling methodology that spans both qualitative and quantitative areas. Okay? And it's feedback-centric, meaning it puts a premium on understanding feedback structure of a system. By feedbacks, I mean these sort of loops, like vicious cycles, but also balancing loops. Types of loops that keep us alive, things like homeostasis, the fact that our body stays in balance, the fact that if we have too little water in our system, we get thirsty, we go get water. If we get hungry, we eat. All right? So there's regulatory loops that are balancing, loops that are reinforcing. In system dynamics modeling puts a premium on kind of understanding that feedback structure as a guide to understanding how systems will behave. It also puts a real premium on representing, including graphically here, what are called the stock and flow structure of a system. So accumulations over time. And here what we see is 3 accumulations. We see a population divided into 3 categories according to a person's illness status. Susceptible, they're susceptible to infection. They're infective, they can spread infection. So they've been infected and they can spread it and they're recovered. Here we divide up a population into 3 stages. In each of these you could think of as an accumulation of some number of people that are in that state. People come into susceptible, maybe through immigration, for example, or birth, and then they're infected and they go to the infective state, and the infective has people who have gotten infected but haven't yet recovered. When they recover, they go here. Okay? So this is what's called a system dynamics model. We see these accumulations, and it turns out that systems like this may look simple, but ladies and gentlemen, they can have complex behavior. So how many people have this on their computer right now? So just trying to see. Okay. Not everyone, but a modest number. So what I'd like to do, now that we've loaded this in, I'd actually like to run a little scenario up here, okay? So if you go up here, and you can actually click in this box here, and you can type in a name of a scenario. This will be a run. It's a simulation where we're going to ask the system to simulate over time how many people are in each of these states over time, okay? And we're going to press enter then. Well, for me it says it already exists, but for you it won't. And press enter and actually simulated it, okay? Now how do I know that? Well, one way I can go like double click on infective, and then I can draw a graph here, okay? And I can actually see how many infective people there are over time, okay? But an even better way, and you folks have a slightly different version, so I'm going to have to peek at one of your screens. But there should be something that's called Synthesim up here. It's just to the right of this, and it looks kind of like a running man with a strong wind behind him or something like that. And you can press on that, and then you'll actually see this sort of behavior shown on top of these things. Do people see that? No? You do. Okay. Okay. So you should see this. And so this actually shows over time how these variables are behaving. Okay. So how many people are in the effective state, how many people are covered, how many people are susceptible. Okay. Now, what's particularly powerful about this and about this tool is that we can change these things interactively. So, for example, we can modify contacts per unit time, infection duration, etc. So, just so that we have some point of reference, what I'm going to do is I'm going to leave this as the so-called baseline. This is kind of our reference scenario. It'll be our default kind of scenario, and we're going to change something. But to do that, we're going to give it a different name, that run. So we're going to be comparing baseline and this other. I'm going to call it alternative up at the top, okay? And I'm going to press enter, and initially it's just drawn right atop the baseline. So green and blue or so red and blue are the same. But ladies and gentlemen, now I could change something. So I can actually, for example, change contacts per unit time by dragging it, okay? And you'll notice things, do you see things changing there? No, you don't see that? Okay. Okay. So let's. Okay. So you have to press enter. Oh. Okay. Okay. That's interesting. So could you go and drag one of these things, and what happens? Like go to this contacts per unit time. This guy here, drag it. Yeah. Yeah. There you go. Yeah. You see that? Okay. So here, what we're doing, folks, is we're changing our assumption about certain features of the situation. In this case, the number of contacts a given person in the population makes. Maybe this is contacts in terms of standing very close to someone so they could spread an infection through the air, or maybe it's sharing needles with them. It could be different things in different circumstances. This is contacts per, it might be 12 contacts per day where they're close enough to really infect someone. We can change the assumptions about that and see how many people, what's the implication all across the model of that. So what it's doing is it's simulating this model over time with this changed assumption. Over time, each of these things is being simulated. It doesn't make that sound. Maybe it's too bad, but it's simulating over time each of these, and it's displaying the results all really quickly. Okay, so here we have a situation where we can modify assumptions about duration of infectiousness, the size of the population, etc., and we could see the consequences all across the entire system. This is a systems model. It's a model that integrates all these different features into one place so we can ask what-if questions. This is a kind of what-if question we've asked. We've asked what if contact rate is higher. So we could alternatively click on this, and I could say I want a contact rate of 20, twice as high as the initial value. And actually, if you go mouse over these things, you'll see actually now we have a situation where the red, this alternative assumption, leads to a much faster epidemic spread in terms of the number of people infected than does the default. Okay. Another way to do this is if we double click here, we can go over and see a graph, and there it labels it more clearly. Baseline is blue, and red here is the alternative scenario. Sorry? Oh, okay. So what I did, it's a good question, what I did here was I went and I clicked on this little line here, and do you see that? And then you can type, you know, I could alternatively say, what if it's half the normal value? How would that change things? And I see, okay, now we have a much slower epidemic. I could say, how if it's just one? And what do we see now? How if I said it's just one contact per unit time? People are only, you know, they're mostly staying inside. They only contact another person. Where's the epidemic now? It's gone. disappear. The infection never happened. Ladies and gentlemen, what we've just seen is a demonstration of a tipping point, a situation where the results of this system can be very, very different, totally qualitatively different under one set of assumptions versus another. Same system, same underlying, sort of thing of how the world works, but our assumptions about the details, for example, how many contacts people are having, can literally make the difference between an infection, an outbreak occurring, taking off, versus one where it just peters out. We go when we look at how many people are actually infected over time here, you could look at this graph and you can't even see it. And if in fact I go and I ask for a table here to show me the number over time, a sort of report, I can see, okay, for this alternative, it's just going down. It's actually decreasing the number from one person starts infective and it never takes off. It never goes beyond that one person. And we'll see why this is. We'll go into explanations about why this is. Okay? This is kind of a first example of a tipping point. In these so-called complex systems which we can't, just by looking at them, understand how they'll behave. We can't, by simple analysis, understand. We have to simulate them. You can get behavior that's very counterintuitive. You wouldn't have expected. The whole is greater than the sum of its parts. In other words, you're getting something very different out than you put in. Something very different from what you would have expected. Okay? These are emergent patterns of behavior. And here we've seen a tipping point. That's one of the aspects of this emergent behavior. We see a situation where we get very different results based on potentially small differences in assumptions even. And we'll see where those things can come from. We'll see more compelling examples. This is an example of a system dynamic simulation model. Now, this is a graphical language used in system dynamics by many packages out there. PowerSim, Vensim, I think there's Stella. They make use of similar frameworks. And if we go and we poke around, you'll actually see there's very quantitative stuff behind here. So if you go to the equations mode, you can, for example, go look. Some of these things are quite simple. Like let's go look. So you see these connections here. What do you think it means that total population here has an arrow from susceptible, has an arrow from infective, and an arrow from recovered? What does that mean that there's an arrow to it? Anyone want to guess? It depends. It depends on those things. What do you think the formula is for total population? Given that people are either susceptible, infected, recovered in this model, it's a simplification of reality. It's just the sum of it. So if you go and you click on it, susceptible plus infected plus recovered. Okay. Similarly, the prevalence of the fractional prevalence, the fraction of the population that's infected. Well, how do you think that depends? What do you think that depends on? Looking by this, it depends on what? And total population. And what do you think its formula would be? If you want to ask what fraction of the population is infective, what would you do? You'd good. This by that. Okay, so go click on the formula and you'll see exactly that. Okay. So ladies and gentlemen, is this a programming language? Is this a programming language? Of sorts. It actually is. It's a declarative programming language. You may not think of it as such because, where's the while loop? Where's the variable declaration? Is that a for? No, you don't see that. You don't see a function declaration. You don't see a public, this field or what have you. Is this a programming? It is, ladies and gentlemen. I'm somewhat from a computer language background. I did quite a bit of work in that area. And this is what we would call a declarative programming language. Okay? It lets you specify the what you want to simulate, and it takes care of most of the how. Okay? Ladies and gentlemen, it may surprise you, but this is what I call computationally universal. What I mean is, actually, any computer program could, in principle, be simulated by a large enough model like this, believe it or not. It wouldn't necessarily be pretty, but you could do it. So it's an extremely powerful way of describing it. let me give you some sense, though, of a little bit of what's behind it. Some of you may prefer to see this thing. I mean, viewing this graphically is really handy. You can go click on things, you can highlight them, you can graph them, and so on. But if you want to see what underlies it in terms of equations, you can do here, go view and, ooh, is it not allow it in the Vensim, in this edition? Excuse me. You should be able to do on the more powerful edition, you can do view as text, and it will show you. Oh, come on. You got to be able to do it in this free version. Oh man. Well, if it's not going to do it, I can open it as a text file and show you. Behind all of this is just a set of equations, and I'm not sure why they haven't. If one of you could find it here, that would be great. But might be able to do it as save as a text. Well, text model no. In any case, behind this is a set of equations, and you can get access to them like this. But you'll notice the stocks. I'll ask you. I'll give you a hint as to what sort of equations are behind this. So I just clicked on susceptible, and this is what I see. What's this thing? Anyone want to hazard a guess? Integration. So it's the integration of immigration in minus infection out. In other words, integration of the inflow minus the outflow. This, ladies and gentlemen, is nothing more or less than we could simply write this as a set of differential equations. Okay. So if I had dx dt equals I minus O, inflow minus outflow, I could integrate both sides of this. I could then take the dt, multiply it over, do the integral of both sides, turn this into x, and this is the integral of I minus O dt. Okay? That's exactly what that is. Okay, ladies and gentlemen, this model, which is this very nice interface and very consistent interface, very simple. You build up a model using this interface. It unpacks the differential equations, which can be understood mathematically. And for those from engineering background, particularly, or physics background, you know there's a huge edifice of stuff that could be used to analyze differential equations. These are what are called ordinary differential equations. Differential equations where you simulate things over time. And there's just wonderful things you can do with them. You can show where the equilibria are. You can identify the stability of those equilibria. You can do an analysis for over what ranges of parameters those things are stable. You can do an amazing amount of stuff with these, given that they're differential equations. But for the most part, most of the people who use this sort of modeling don't by and large do this. They work within this framework and they run simulations and they view the results, and they don't have to go into the math unless they really want to. Okay, so there's this underlying math here that's very rigorous, but there's also this really nice graphical interface that allows you to explore it declaratively and keep your attention as a modeler focused on the modeling level issues rather than on the vagaries of exactly how it's implemented. Okay? So this is one package. We're going to take a glimpse of another package, okay? And this will be the final thing we do today. So I'm going to close this model. I think, by the way, I'm going to refer you to a video where we build up a model like that. You can build up a little model at home. Okay, so next I want to go to AnyLogic. I'd like to call up AnyLogic. I'd ask those of you who are here a little bit early to do that up. And when you come up with AnyLogic, you may come up with this screen to start with that says welcome. If you don't, you can go to help and you can go to this welcome screen, or you can go to example models, okay? Either one of those are fine. And I'd like you to go down, ladies and gentlemen. So I should probably nuggetize that. Kurt, I need you as my nuggetizer.
I need